Okay, so let's look at an example that utilizes this equation that we just derived in the previous video. Here we have this collar that is moving down with a velocity vc equals 2 meters per second, which means this is going to push b out this way, velocity of b in this direction. Let's do something else. Let's put in here a coordinate system. So let's go y this way, x this way, and z is out of the board towards us. So what we want to do here now is we want to find the angular velocity cb. So we want to find the angular velocity of the green link. Well, we can of course use the above relationship. Let's rewrite it in terms of our letters. So the velocity of c equals the velocity of b plus the velocity of c with respect to b. Now, as a side note, we could have done the velocity of b equals the velocity of c plus the velocity of b with respect to c. And the difference in our setup here is the directions that our different position vectors go. That are the position vector rb with respect to a, which you'll see makes a difference here in a few seconds when we work this out. So this equals the velocity of b plus, remember that we can do this as omega cross r of c with respect to b, because the velocity of c with respect to b is not necessarily easy to figure out. So at this point, it's useful now to set up our position vectors. So we have RC this way. So I'm going to go from the fixed point A, notice A is a fixed point, to shoot my position vectors. And we go down here to RB. Now remember, these are positions, not velocities. So it's just the coordinates essentially of these. And the direction of our RC with respect to B is this way. We have to move this way in B, we move down in B, and then we move up in this direction in RC with respect to B to get to the same point that we would get to if we just went straight across at RC. So that way we have the same relationship. Notice that if you reverse this equation, this vector would point in the other direction. So there would be a small difference in your relationships, your equations. So let's put the values in now here. So the velocity of c is, according to our, it's negative of y. So minus 2 meters per second in the j direction. And the velocity of b is to the right. So I'm just going to use the magnitude of b times I plus omega is what we're looking for, our angular acceleration. It's probably going to be in this direction. So I'm going to make omega positive k because my thumb is pointing out of the screen when I rotate that way with the right hand rule. And then we get our position vector, r. And with r, we head in the negative direction of I of 0.2, so we head 0.2 this way, and then we have 0.2j in this direction, and that's what r is. See, it's 0.2, 0.2 here, and then 0.2 up from here. Okay, so we've got everything all set up. Notice we have two unknowns here in this equation, velocity of b and omega. We're looking for omega, but let's see how we'll deal with that. First off, let's calculate this, velocity of b We don't need vector signs here anymore because we're using this representation plus. Now, if you look in the back of your Hibbler book, you'll see there's a section on cross products, dot products, I think. There certainly is one on cross products and operations in cross products. So we've got a simple vector here that is being that we take dot omega and cross that simple vector. So we can distribute this. So this is omega times 0.2. Now this is k. So think of our axis again. So this is k cross I. So k cross I, that's going to give us a positive j. So this is positive j, but there's a negative on our point 2. So this is a negative value. Yeah, we'll just write the negative here. Minus. Okay, and then we've got, actually let me write this out. So I distributed now this cross product, and again our first term here turned out to be minus 0.2 omega. K cross I is j. Now our second term, k cross j, this is going to be minus I. So again, this is going to be minus, this is going to turn out to be an I, and this is 0.2 times omega. So writing this whole thing down here, meters per second j. So now we have a relationship with both I and j terms. Let's just combine the coefficients of each term. So let's look at the I terms first. We get 0 equals VB minus 0.2 omega. So these are the I's. The I's have this. So from this, well, let's continue on. And then we have the j terms. We have minus, oops, no fatties. We have minus 2 meters per second j, and then we have this equals minus 0.2 omega. So now we have two equations and two unknowns. Actually, this j equation only has one unknown in it, so we can solve directly for omega here without even have to use a system of equations. And omega here, these are minuses on both sides, so we're going to have a positive value. 2 divided by 0.2 is 10. So 10 rads per second, and my guess for the direction is correct. So it's heading in this direction. And over here we have the velocity of b then equals, if we wanted to calculate this, I guess this isn't part of the problem, but this will end up equaling, when we put 10 in here, 2 meters per second in this direction. And that is the solution to the problem right there. So the thing spins to the right with 10 radians per second, and the velocity of b is 2 meters per second. Okay, let's do another one. So this is 1666 in your book. And all right, so if the angular velocity of AB is 4 rads per second as shown here, let's find the angular velocity of CB. Okay, so let's use the relationship we developed. Velocity of C equals the velocity of B plus omega cross position of C with respect to B. Okay, I'm going to guess that the velocity C is heading down here, and the velocity of B, since this rod is spinning around this fixed point here, is going to be perpendicular to this. let's decide to use this as y and this as x. So if this is our axes, if we set this up as our frame of reference axes, I can make a little triangle like this and figure out that that is 30 degrees up here. Since this is 30 degrees, it has to be the same. This will help me determine the velocity of B, the components of B in x and y component, or I and j components essentially. So the magnitude of the velocity of B is going to be the radius times our angular velocity of 4 times 0.5, and then that will multiply by minus cosine of 30 I, because we're heading in the negative direction, plus the sine of 30j. Okay, that's our velocity of B. Let's look at C now. So we don't know what the velocity of C is, but we do know that we could take the magnitude of C and multiply it by cosine of 45 degree I minus, so these are both minus sine of 45 degrees J. Let me make room for all that. Okay, so I moved it down. So now we have the velocity of C, the magnitude of the velocity of C, which we don't know, times. So it's heading in the negative I direction and the negative j direction. That's the trick for that. And I just copied the velocity of B back down here. So now I add omega cross R, omega that we're interested in. So this is going to be omega of our BC. We're going to assume it's spinning this way, which means that we have K and K cross, let's just put parentheses here, even though we don't need it. Let's just put parentheses here, K cross. So the position of this is horizontal, and it's in the I direction. It's going to be minus 0.35 meters I. So K cross I, remember Z is going to come out of the board here, so it's K cross I gives us a J. So this is going to end up being a J term here, and minus 0.35 times omega, so minus 3.35 omega J. Then let's do this calculation from up above here for velocity of B. So we end up with this. I just made the J's red so they would stand out. And then over on the left side we have this, and let's make the J's red again so it stands out, because we're going to group these values, I's and J's, to solve our problem. Again, we're stuck here with two unknowns, VC and omega, and this is omega BC that we're interested in, but we'd also like to know what the velocity of C is too. But we can do both of these because we can group terms. So the I term first, and as it turns out there's only one unknown here, and we can solve for it. So VC equals 2.45. Turns out to be positive, which means our direction was correct. And now if we group the J terms, we'll substitute in VC of 2.45, sine of 45 equals 2 sine of 30 minus 0.35 omega BC. We solve for omega BC, and omega of BC equals 7.81, and it's positive, so we're correct in our direction. And that will be our answer.